right, you guys. I'm going to walk through the problems in this section just one by one, kind of just demonstrating how you do this trig. So I'm pulling out a graphing calculator so I can do the calculations off screen. If you have trouble working on calculator, I could always make a video of that or help you in person once COVID is over. Okay, so let's do this. Ready? So in this first problem, we just literally have a right triangle where we have the angle and then we have the opposite side and the hypotenuse. And so we're going to use our SO of SOHCAHTOA. So the sine of 32 degrees is equal to the opposite side A over 17. So multiplying both sides by 17, we get A is exactly equal to 17 times the sine of 32 degrees. And then we could say it's approximately equal to, that's this wavy approximate up there, 17 times the sine of 32 degrees. You should get 9.0086 yada yada. So it's rounded to 2 decimal places. And let's say it's around 9.01, okay? And that's in centimeters because the original was in centimeters. Now, just to double check, you should be able to put in your calculator sine of 90 degrees and get 1. So you can always double check that when you pick up a new calculator. And that means you're set to degrees. If that comes out to be like 0.86, that means you're just set to a different form of measuring angles, which is called, oh, look at me, there's a little picture of me. Haha, let's get rid of that. Okay, so that's set to radians then. And so you can just change that setting from degrees to radians in your calculator settings. All right, so let's do the next problem. Here we got parallel sides, we got a right angle, and so we're just looking for this angle here. So this is the opposite side over the hypotenuse. So what that means is we've got the, whoa, I almost wrote tangent, O and H, that's the SO of SOHCAHTOA, that's sine of x, equals 18 over 20. If you wanted to reduce that, you can. So sine of x is equal to 9 over 10. Now, exactly rewriting this, we could get that's equal to, or that's the equivalent to, x is the arc sine of 9 over 10, or depending on your book and your calculator, that's the same as inverse sine of 9 over 10. So all three of these expressions are equivalent. We just use this inverse sine or arc sine to find an angle measure when it's missing. So that's the exact expression right there. That's exactly right, or so is the arc sine. Those are both correct answers. But if we want an actual angle, we plug that in and we go, okay, well, the second button sine, so that's inverse sine of 9 divided by 10 ending my parentheses, is about 64.158 ... degrees, or x is around 64.2. It didn't specify what we should round to. So this was over 5 or over, so we rounded up there. So either approximate or equal. Let's go to this one. So if you haven't done circles yet in some classes, depending on order, anytime we have a diameter of a circle, this inscribed angle is half of the 180 degree arc, so it's always a right angle here. So we did know this was a right angle. If you don't know that about circles, then just skip that problem for now. All right, so looking at this now, we've got 32 degrees, we've got the adjacent leg, we've got the hypotenuse here, isn't r, but the hypotenuse is 2 r's, right? So 2 radiuses, and then we don't have anything to do with the opposite side. So we're looking at the cosine here, right? So SOHCAHTOA. So we've got cosine of, erase that, so we've got cosine of 32 degrees is equal to the adjacent side 12 over the hypotenuse 2r. We want to solve for r. Well, we can just reduce that thing on the right. So this is cosine of 32 degrees equals 6 over r. That might make it easier. Now let's multiply both sides by r, right? That cancels. We get r times the cosine of 32 degrees equals 6. Now remember, the cosine of 32 is just a number. So I see this as 3r equals 6. Now 3 isn't the actual number, but it's just a number times r equals a number. So we just divide both sides by whatever number is multiplied by r. So here the number is cosine, so I'm going to divide both sides by cosine of 32. Right, so on the left, that exactly cancels out. That's why we did it. And we get r equals 6 divided by the cosine of 32 degrees. That's the exact value, but it's approximately 6 divided by cosine of 32 degrees is about 7.075 ... Okay, Now we're looking for E here. Well, parallel lines stay the same distance apart forever, so we could slide this vertical distance between to right here. So here's a right angle, and this is still E. And so we get that we have a right triangle with a 62 degrees. An opposite side is E. The hypotenuse is 27. So we get the opposite over hypotenuse is the sine. Why do I keep writing tangent? What the heck? The opposite, as my mouth is speaking. So opposite over hypotenuse is the so in SOHCAHTOA. So it's the sine of 62 degrees equals the opposite E over 27. Multiplying both sides by 27, we get E is equal to exactly 27 times the sine of 62 degrees. And that's approximately equal to, and in a calculator, 27 times the sine of 62 degrees. That's 23.839, ... Okay, and you round to whatever amount you want here. All right, so in this one, we have a kite. Now, with CP/CTC, you could prove this, or we just know that kites have perpendicular diagonals. You could just prove that this triangle is congruent to this triangle by SSS, and then you just go, well, then that means these angles are the same, these angles are the same, and then you could go, oh, wait a second, that means this triangle right here is congruent to this triangle by SAS. That means this angle matches this angle, and a linear pair with the same angle must be 90 plus 90 equals 180. Those are only two congruent angles that add up to 180. So you could prove this pretty quickly, but we just know that, okay, from our work with quadrilaterals. So it's asking for the length of diagonal 1. Okay, diagonal 1 is that total thing. Well, this is a line of symmetry, right? By SSS, that top triangle and bottom are the same. So this is just D1 over 2. This is half of D1. And so in this triangle here, if I redraw this, we got a 56 degrees, we've got an adjacent leg, and we've got the hypotenuse. We know the hypotenuse is 20, and this one's D1 over 2, and we want to solve for it. So we get that the cosine of 56 degrees is equal to the adjacent leg, D1 over 2, in parentheses, all over 20. Okay, now I could just simplify this right side. One way to think about it is, I'll do it up here, D1 over 2 divided by 20. That's the same thing as divided by 20 over 1. D1 over 2 times 1 over 20. So that's D1 over 40. That's what this comes out to be. Okay, so we got the cosine of 56 equals the length of diagonal 1 divided by 40. So we just multiply by 40. And we get the diagonal 1 is exactly equal to 40 times the cosine of 56 degrees. Okay, or that's approximately equal to 40 times cosine of 56. That's 22.3677 ... And you can round to whatever you want. Okay, so F here, we're trying to find that angle. Well, this is an isosceles triangle. So when you cut an isosceles triangle in half with that altitude, it's also the angle bisector, it's also the median, it's also the perpendicular bisector, it's the line of symmetry. So that cuts this into 14 and 14, right? You could do that in lots of different ways. So one way you could tell is these two triangles are congruent by right angle, hypotenuse, leg. So by HL, those two triangles are congruent. So everything's congruent, including these side lengths down here. So 14 and 14. All right, so what that means is we've got a 16 and a 14, and we're looking for the angle. So if we have, whoops, I just wrote that, I meant F, and we're looking for the angle there. I just redrew it for no apparent reason, right? Here's the opposite, here's the adjacent. What are we using? We're using the tangent. So I'm going to shrink this and move it off to the side. And so that's tangent of F is equal to opposite side 16 over adjacent side 14. We could simplify if we want. And so rewriting that exact expression, F is equal to either you write it as the arctan of 16 over 14, or you write it as the inverse tangent of 16 over 14, or you could reduce it and it could be 8 over 7. Doesn't matter. You get the same value either way. So F is exactly equal to this, but it's approximately equal to, we plug it into our calculator, and the inverse tangent of 16 divided by 14 is 48.8. 814 dot 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 dot. Okay. All right, this one, it looks really scary. Whoa, 3D shape. What am I going to do? Panicky and heart palpitations. Okay, no, just kidding. It's just saying, what's that angle? Well, all we need to do is really find this angle here. It gives us a right triangle, so there's no 3D involved there. We have a right triangle with x, 12, and 16, and then we just find its linear pair, so 180 minus x. That's it, easy peasy. So here's the opposite side. Adjacent side, so that's TOA, so tangent of x equals 16 over 12. So that means, rewriting it, that means x is exactly equal to the inverse tangent of 16 over 12. Just rewriting that same expression, right? These two are equivalent statements, just one's the forward, one's the backwards. Okay, so then we get that's exactly the value. Or you could say, oh, that's not the answer, we're not looking for that. Good thinking. Okay, so our exact answer is theta is exactly equal to 180 minus the inverse tangent of 16 over 12. And yes, you could reduce that. All right, so that's exactly the value, or that's approximately. So in my calculator, 180 minus the inverse tangent of 16 divided by 12, that is 126.8698 dot 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 degrees. Okay, let's look at this other one. Oh my God, it's so scary. Panic. Just kidding. They give us a right triangle. It's okay, you guys. Look, and we're looking for an angle, and we already have the opposite side, right? All we need to do is find some other side. Well, right here, if this is a right angle, which when they draw this, we're assuming it's a rectangular solid with right angles at every corner here because it's a rectangular solid. So that's the assumption we're making. They should have told us it's a rectangular solid, but whatever. Okay, so what we know then is we could use 8 and 15 to find this hypotenuse length. But I know that 8, 15, 17 is a Pythagorean triple. So this is a side length of 17. Or you could arithmetic that out with 8 squared plus 15 squared equals c squared. But knowing you're like 3 common Pythagorean triples of 3, 4, 5, all the multiples, 6, 8, 10, etc., and then 5, 12, 13, and 8, 15, 17. Those are really the ones to really know, but also 7, 24, 25 comes up once in a while. All right, so anyways, now we've got this triangle, which looks like this. We got a 10, a 17, and an angle we're looking for. And so that's the opposite side and the adjacent. So it's exactly the tangent. So tangent of, I'm not going to use theta actually. I'm going to use their like Greek letter B. I'm assuming it stands for beta, but I don't know. So tangent of cool looking B equals 10 over 17. So rewriting that, then that cool looking B is exactly equal to the, let's use arctan this time. Just switch back and forth. We're comfortable with both. So arctan of 10 over 17. And so that's the exact value, and it's approximately equal to, so the inverse tangent of 10 divided by 17 is 30.4655 dot 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 dot. Okay. Oh, what about this one? Ooh, crazy. Panic. Ooh, 3D. Just kidding. They just give us a right triangle. We always measure the height here. Now it's implied that there's the H is standing for height, and height is always measured perpendicular to the base or whatever you're measuring it from, and so this is the base of the polygon. So that's a right angle. So now we have tangent of 58 degrees equals height over 40. And so we just multiply both sides by 40. That cancels, and we get the height is exactly 40 times the tangent of 58, or h is approximately 40 times, I wrote 41, times tangent of 58. There we go, that's 64.0133 dot 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 degrees. Okay, or not degrees, that's height, that's in centimeters. Okay. Now let's get to some word problems. According to a Chinese legend from the Han Dynasty, oh my gosh, can you even imagine? I mean, that was thousands of years ago. Like, what was daily life like back then? So cool. Okay, so this general flew a kite over the palace of his enemy to determine the distance between his troops and the palace. I'm assuming he got some sort of weapon he's got to like shoot that far. So the general let out 800 meters of string. So here's 800. And the kite was flying at a 35-degree angle. Then how far away was the palace? So what was the distance there? Now, we're assuming the kite was exactly straight, but that's not the way string works. String droops. It has a weight. It's natural that it droops. I mean, unless you were pulling with thousands of pounds of force on both ends, but even then the string would just rip asunder, just all the threads coming apart in slow motion. That'd be pretty cool to watch. Anyways, so here we go. This is the adjacent side. This is the hypotenuse. So that means we have the cosine, the right, so ka toa, which is adjacent over hypotenuse. And so we get the cosine of 35 degrees equals the adjacent side distance over that hypotenuse of 800 of string, 800 meters of string. So then we just multiply by the 800 on both sides, and we get the distance is exactly 800 times cosine of 35, ignoring the droop of the string. And so we get the distance is about 800 times the cosine of 35 degrees. Okay, and physics can actually tell you how much that string is going to droop, which is pretty rad. So when you get to Newtonian kinematics and tension and force, you can actually calculate how much that's going to be. But you get about this many meters away. Okay, so the next one. Benny is flying a kite directly over his friend Frank, who's 125 meters away. So here's 125 meters. That's always a height. When he holds the kite string down to the ground, the string makes a 39-degree angle. How high is the kite? So what's the height? So in this case, we've got the opposite side and the adjacent side. So that means we're dealing with the tangent of 39 degrees equals the opposite side over the adjacent side. That's toa. And so then multiplying by 125 on both sides, we get the height is 125 times the tangent of 39 degrees. And so the height is approximately 125 times tangent of 39. That's 101.2230 . Okay? So again, exact and approximate. All right, so the angle of elevation from a ship to the top of a 42-meter lighthouse on the shore, 33 degrees. How far is the ship? Okay, and assume it's level. So this is just a straightforward. We have an opposite, we have adjacent. In height is always measured with a right angle. So we have tangent of 33 is equal to opposite side, 42, 42, over adjacent side, y. So we multiply both sides by y. That cancels with that. Now we have y times tangent of 33 equals 42. And again, this is just a number. So we just divide by that number on both sides because it was multiplied by y. So the opposite's division, right? And so those cancel. And we get y is exactly 42 over the tangent of 33. Or in other words, y is approximately 42 divided by tangent 33, 64.6743, ... Okay, let's go on. So now we've got 13 here. A salvage ship's sonar locates a wreckage at an angle of depression of 12 degrees. So here's a boat. Okay, 12 degrees down. It says, okay, we see something. So they lower a diver 40 meters to ocean water. How far does the diver need to walk, assuming it's flat, to get to the treasure? So here's the treasure chest. Whoa, how do you draw a treasure chest? I don't know. There's the treasure chest. And so you're looking for this distance. Well, remember, horizontals are always parallel, so alternate interior angles. The angle of elevation, angle of depression are always the same. So really we have the opposite side, and we're looking for the adjacent. So that's toa. That means the tangent of 12 degrees is equal to the opposite 40 over the adjacent distance. And so I'm going to switch colors here. So multiplying by distance on both sides, we get distance times tangent of 12 equals, those canceled, we have 40. Then we just divide by this number on both sides, so dividing by tan of 12 on left and right. It cancels out on the left. That was the whole reason we did it. And we get the distance is 40 over the tangent of 12 degrees. So that's the exact value. We could say that's approximately equal to, punching in the calculator, 40 divided by tangent of 12 degrees, which is 188.185, ... And you can round it to anything you want it. All right, so a ship's officer sees a lighthouse at a 42 degree angle to the path of a ship. Okay, so here's this ship, okay, and it was going this direction, and there's a 42 degree angle, so 42 off to some side. He sees a lighthouse. So here's a lighthouse, okay? Woo, and then there's a light at top. After the ship travels 1,800 meters, so he goes forward 1,800, the lighthouse is at a 90 degree angle. Oh, so he went all the way to here, and there was a 90 degree angle now, right? The ship's path is this way, and now there's a 90 degree difference. What's the difference between the ship? Wait, what's the distance between the ship and the lighthouse at the second sighting? So in other words, what's this distance here? Let's call it x. Well, it's just a right triangle where we're looking for the opposite side. We have the adjacent side. So that's, again, TOA. That's tangent of 42 degrees equals the difference now is that the x is on top, which makes it a little easier algebraically because we just multiply both sides by the 1,800 meters. And we get that x is equal to, because on the left that cancels out, exactly 1,800 meters times the tangent of 42 degrees. So that's going to be about, right, 42 degrees is about 45, so those are about equal, but a little smaller, so maybe like 1,700. Just, it's helpful sometimes to ballpark, so you know whether you made an algebraic mistake somewhere. So tangent of 42, so 1620, okay. And then 0.727, ... All right, and again, you could do exact or the approximate. All right, so meteorologist shines a spotlight vertically into the bottom of a cloud. So here's a cloud. Whoa, here's a cloud. And so he shines straight up. So vertical is right angle with the ground. He then places an angle measuring device 165 meters away and measures an 84 degree angle. That's a really steep angle. This is going to be really tall. How high are the clouds? So let's call this height. So again, this is TOA. So we got opposite over adjacent. So we have tangent of 84 equals h over 165. So multiplying by 165 on both sides, we get that the height is 165 times tangent of, I wrote 80, it's 84. I don't know why I wrote that. Let's change that. And so that's exact, or that's approximately, ooh, this is going to be a big number. What is it? 165 times tangent of 84. That's, 1569.870, ... Okay, next one. Meteorologist uses a theodolite. So this theodolite picture's on the left. It's just basically a telescope with a protractor under it. So it measures what angle you're looking at. Okay, and on a 1 meter tall tripod, so it's off the ground by 1 meter, to find the height of a weather balloon. You see boost balloon, so from this, there's a 44 degree angle. All right, and the radio signal from the balloon tells her that it is 1,400 meters from the theodolite. So I'm assuming that's horizontal. Let's see. No, because here it's then saying how far from the point directly below. That's question B. So it's not the horizontal distance. So they mean actual distance. So that's probably a timed signal. So they could tell how long it took for the signal to get from the satellite to the theodolite. And so it's 1,400 meters away, just, distance in 3D space, a straight line distance. And then the question, the first one is, how high is it? So remember, we got to add the 1 meter at the end. So we got to find this height and then add the 1 meter. So it's about, right, a 45-45 triangle. So we can kind of just divide this by root 2 to approximate. But we're going to figure that out. And then we need to find this distance here. That's question 2. How far are they from the distance directly below the balloon? Then if Wendy's theodolite were on the ground rather than the tripod, would your answers change? So the only difference would be the height would be 1 meter difference, which probably isn't going to be a huge difference. But the horizontal distance wouldn't change, because if you drop that right triangle down, you still get the same horizontal length there. Or do you? No. It would even be a little bit further back, because for it to have a 44-degree angle, it would be like this. And so, yeah, it would be moved back. So you would get a different value for both, right? Let's check it out. Let's see what we get here. Okay, so anyways, so for A, we get this is the opposite over the hypotenuse. So we get, that's sine, so katoa. So sine of 44 degrees equals h over 1400. And so we get times by 1400 on both sides. We get that the height is 1400 times the sine of 44 degrees, and then we go ahead and at the end we add 1 meter to it because this was 1 meter off the ground. So that's approximately, so 1400 times sine of 44 degrees, and then we just go ahead and add that one, and so that's 973.521 ... Okay, and then the horizontal distance we do very similar, except this is the adjacent. I'm going to use the starting value just in case we made a mistake with the height. We always want to try and use the given values. So here we have cosine, the ca, adjacent over hypotenuse. So cosine 44 is adjacent side distance over hypotenuse 1400. So we multiply by 1400 on both sides. This time we don't need to add the 1. And so we get the distance horizontally is 1400 times the cosine of 44 degrees. Okay, and so what we're going to do is go, this is, just punch it in. All right, so this one is about 1007.075, ... Okay, so the question is, would either of these change if you dropped it down? So if you had been measuring this from the ground, right? Now the question is, was on the ground, would your answers have changed? So if it was on the ground, that means the satellite would actually be lower to get a 44-degree angle for these lines to be parallel, right? It would be exactly 1 meter lowered here. It would be 1 meter lowered up here. So instead of 973, we get 972 ... But we'd still have the same 44 degrees, the same 1400. So we'd still get the same horizontal distance. The only difference would be that. Now, if we had the satellite in the same place and the theodolite lower, really what we would get is we just get something like 44.1 degrees. It'd be a little bit bigger because we'd have to be looking up a meter higher. But if we were given this value and this value and the theodolite was on the ground, that would mean we get different height because the balloon would be exactly 1 meter lower than where we calculated with the 1 meter off the ground. Oh, and that was the last one. All right, guys, I hope you enjoyed the video.